Okay, hello everybody. I think we're right on time. Welcome to our nice talk, 140th. Today, we're going to talk about, we're going to discuss a very interesting topic, adaptive collaboration with humans for multi-agent language models. And our speaker, Wei Yang, is a PhD student at the University of Southern California, and I'm today's host. Wei Yang is currently a PhD student in USC, and basically his research direction is on efficient collaboration among multi-agent language models, post-training of agentic language models, and multi-agent reinforcement learning. And his current work studies how to improve the efficiency, reliability, and scalability of multi-agent language model systems for complex tasks. I'm today's host. Basically, my research direction is on trustworthy AI, human-centered AI, and personalization. So without further ado, let's welcome Wei Yang to present today's work, which was also accepted to iClear this year. Yeah, Wei Yang, you can share your screen and all is yours now.
Yeah, sure. Yeah. So hello, everyone. It's a great honor to be here to present today's work. And thanks for the invitation. And today I'm gonna to talk about adaptive collaboration with humans, metacognitive policy optimization for multi-agent LLMs with continual learning. Because we know that multi-agent LLMs are widely used in current a lot of downstream tasks. And the core mechanism or the core challenge is how can we broaden the capabilities of the multi-agent LLM systems. So one way is to incorporate the human beings. Therefore, in today's presentation, I will talk about how can we combine the multi-agent LLM systems with the real human beings. So let's get started with a basic concept, the multi-agent LLMs collaboration. So we know that LLMs are already widely used a lot of downstream tasks. And in recent years, multi-agent LLMs began to get a more focus down. And such as the finance agent, generative agent, and AutoGen, a lot of famous works are proposed to solve some complex tasks. So although we know that the multi-agent LLMs has already gained a huge performance in a lot of applications, but there are still several main issues. So first of all, the single LLMs struggle with contextual deduction and the reasoning fatigue when facing non-horizon multi-step tasks. So trying to make one model be the architect, coder, and tester simultaneously degrades performance. And second, single models suffer from self-delusion. It is intrinsically difficult for the model to robustly critique its own output without bias. And for example, the echo chamber effect, leading to uncorrelated errors. So although the multi-agent collaboration can enhance the ability of single large language models, but still we know that why multi-agent collaboration still hits a ceiling. So currently, modern multi-agent schemes, such as debate, graph correlation, self-critique, mainly recombine what the model already knows. They improve internal consistency, but rarely create new knowledge. And especially in out-of-distribution problems, high-stakes domains, or fast-changing facts, agents can converge to a wrong consensus, like the collective hallucination. So it makes the errors more confident and harder to detect. So we need to consider what the real requirement is. So to be reliable in open world settings, an agent system needs an external competence interface, a way to avoid catastrophic failures now and acquire missing capabilities over time. And human experts are not merely a fallback. They are the only mechanism to break the knowledge horizon when the system's internal search is fundamentally insufficient. So here comes to the core tension, reliability versus cost. We know that ask for a human's help is accurate, but it's still very expensive. We cannot always ask humans' help. Otherwise, we don't need the multi-agent systems. And this kind of trade-off cannot be solved by static heuristics because confidence is often miscollaborated and consensus can be misleading. So we need a learned metacognitive policy that decides when autonomy is enough and when deferral is worth it. So based on above analysis, we can arrange our research questions. So first of all, we need to define that when to defer for humans' help, decision under uncertainty and social signals. So basically speaking, people will think about once the large language models generate some reasonings with no confidence, and then we can ask the large language model to ask for humans' help. However, in the multi-agent systems, agreement is not evidence. It can be a symptom of shared bias. So the policy must infer a structural competence state, which is composed of the self-reliability, like the uncertainty, collaboration, and also the group dynamics, such as the diversity versus the brittle and consensus. The third one is the expected failure cost versus the inquiry cost. And the last one is whether the task demands new reasoning path rather than more discussion. So when to defer to humans' help is not a purely simple low confidence for task definition. We should consider the self-reliability, the group dynamics, and also we need to consider whether should we incorporate more reasoning path so that we can broaden the reasoning process. And once we can figure out when to defer for humans, another key problem is, can we learn from the humans' knowledge so that we can enhance the large language model itself? So most humans loop setup treats the expert help as a one-off pitch, and the system stays dependent and does not improve where it works. So a deferral event is an explicit marker of the system's knowledge boundary, and the key is to convert expert feedback into training signals so that for future episodes require less human help. So we can regard this as a loop. Multi-agent systems can choose to ask a human's help once it cannot inference very accurate. At this moment, one of the agent can choose to ask humans help. And once the agent gets a feedback from humans, how can the model further improve itself so that in the future, it do not need to further ask humans help? So here comes to the core technical thesis. We must jointly optimize a metacognitive control policy and a learning mechanism that absorbs expert demonstrations to shape the competence boundary outward. So this is the overview of our work. We want to propose a closed loop for reliable, growing collaboration between multi-agent systems with human beings. So our framework is designed to build a closed-loop agent system that can operate autonomously, decide when to defer to a human, and learn from that intervention to reduce future reliance. So for example, this is a single agent self-reflection pipeline. Once we get the questions, the agent will do the reasoning and reflection. And second paradigm, here we just use the multi-agent debate as an example. We can see that different agents can talk with others freely so that they can share their last round's reasoning and they can talk about some details so that they can further revise their own reasonings. And also there are a lot of graph-based models to optimize the communication between different multi-agents. Like we can build up the communication path as a communication graph, and then we can do the graph modeling or like the graph pruning so that we can further improve the efficiency of communication. And the last one is about our paradigm, the adaptive collaboration with humans. So here, for example, we have defined 5 agents, and each of the agents can do the self-reasoning, and also it can communicate with other agents. And besides, we have some human beings. Once one of the agent can are not quite sure about its own reasonings, or it feels with no confidence, at that moment, the agent will choose to defer for human. And once the human get the request from one of the agent, it can give the feedback, such as the reasoning or the answers for the current question. And except for the human regarded as the requested object, the human can also give the reasonings or give the guidance in the beginning, because we can manually input or we can manually set up some like predefined knowledge so that the multi-agent systems can work with a priori knowledge. Therefore, our system is composed of two directions. One direction is the agent can choose to defer for human. Another direction is the human can actively provide some priori knowledge. So generally speaking, it is composed of three main parts. One is multi-agent autonomous reasoning, and the second one is metacognitive control, and the third one is strategic deferral with continual learning. So first of all, we need to define the state space about these multi-agent frameworks, because we want to build up a very good decision process for the multi-agent so that it can decide when to defer for human and when to trust itself or when to trust one of other agents. So in the beginning, we need to define the state space very well. And this kind of state space can not only be composed of the question, the last round's reasoning, but also it should contain some like well-defined structural cognitive information. So basically speaking, we can define it from two aspects. The first one is the reasoning context information, which is mainly composed of the task definition, the self-reasonings from the last rounds, and also the reasoning information from the peer agents, so that we can get the whole context information about the task itself. So besides, we are still considering if we do not manually design a structural cognitive state space, and then the model is still very easy to be misled by the noise information contained in the peer contexts. For example, we observed that once most of the agents did some like wrong reasoning, and the current agent is very easy be misled by the others' wrong reasonings. Therefore, we need to further introduce some like structural cognitive state to provide more comparison information for the LLM so that the agent can not only look at the reasoning information, but also look at the structural cognitive information. And for second part, the structural cognitive information, which is also combined from several aspects. The first one is the group consistency. So for the group consistency, it is mainly used to measure the consistency between different agents. Because we are in the multi-agent definition, we need to figure out how is the difference between different agents. Therefore, in this kind of group consistency, we defined several signals, such as the majority answers, and whether the majority answers is right or correct, and also such as the majority answers diversity, so that we can use this kind of metrics to describe the group consistency. And second, we define the self-reliability, which is mainly used to describe the reliability features of its own reasonings, such as whether the agent generated the required format, like the reasonings and also the answers, or whether the reasoning is completeness. So we also introduce several signals to describe the self-reliability of the current agent's state information. And last is about some like the other selective signals, like we can compare the current agent with some like strong agents, which is recognized from some manually designed rules or from the trust information, like the confidence information, so that we can further introduce some selective signals. So once we constructed this kind of reasoning context information and structural cognitive information, we can combine these two together to format our whole cognitive state space. Like we concatenate the task, the self, and also peer context with the group consistency, self-reliability, and the comparison information together. And then we just input this data information into the LLM systems. Okay, and then it comes to the action space, because we proposed the core issue when to defer for human and when to trust itself or when to trust one other agent. Therefore, we defined this kind of two-stage decision process or this kind of two-stage decision reasoning. And the first stage is mainly do the high-level decision reasoning, and for the second stage is mainly to do the execution reasoning. So for example, here is agent Bob. We ask the Bob with a mathematical problem, and then the Bob should decide the strategic actions first. And here we define three kinds of actions. The first one is evaluate, which means it does exploit the collective knowledge, which means the current agent can use the current reasonings from all of these agents, because we can look at the questions, we can look at the other agents' reasonings, so we can figure out which of the reasoning is more reliable. Therefore, for this first action, which means we can choose one of other agents' reasoning as our own reasoning, and we do not need to do any further LLM reasoning later. We just only need to copy one of the other agent's reasoning. And the second action is to do the create, which means creative exploration and hypothesis generation. Like, since we already look at others' reasonings, and each agent has its own like last round's reasoning, so we can compare its original reasoning with other agents' reasoning, and maybe it can find some like detailed errors of itself in itself own reasoning, so that the agent will choose to like revise its reasoning with the information from other agents. So the second action mainly focus on the creative exploration. And the third one is the defer for the human, like we just do the risk mitigation and knowledge augmentation. That means once the agent feels lower confident, it will choose to defer or help from the human. So once this kind of Bob agent choose one of these actions, we comes to the second stage. And the second stage is the classical LLM reasoning state process. Like for the first strategic action, and then we will directly copy the chosen agent's reasoning and answer. And once the agent decide to create, the agent will do the revision based on the last self-reasoning and also the reasoning from other agents. And the last one is about the revision. Last one is directly get the reasoning and answers from the human. So here is our action space definition. Okay, and then it comes to our learning part and our method part. So once we already defined the state space and action space, because we want to automatically train the model so that the agent can automatically choose when to defer a human and when to trust itself or when to trust one of other agents. Therefore, we want to introduce the reinforcement learning to train it so that after the training, the model can generalized to a lot of other downstream tasks rather than only based on the prompting heuristic paradigms. Therefore, we need to build up a very well-defined reward function so that our model can be further trained by this kind of reinforcement learning process. So in the beginning, we need to define this kind of reward function. The purpose is to learn a cost-risk trade-off for deferral. Therefore, this kind of reward function is mainly composed of two parts. The first part is about the reward related to the predicted results with the ground truth. Because finally, after n rounds collaboration, we can get the final answers about corresponds to a specific question, and then we can calculate the correctness between the predicted values with the ground truth so that we can get the final reward from the predicted values. And once we choose the defer action, we can get the reasoning and answers from the humans. So therefore, the first part is about the predict values so that we can get this kind of rewards from predict values. And the second part is about the cost, because we know that once we directly copy one of others agent's reasoning, it's free, right? Because we already have it. But once we decided to revise our last round's reasoning, or we decide to ask a human's help, it should cost, because we cannot always ask humans help, and we cannot always to do the revision because it with some of the tokens. Therefore, we need to introduce the cost of the actions so that we want the model learn cost and the performance trade-off rather than always ask a human's help or rather always like do the revision. So here we also defined the cost reward, like for the create action and also for the defer action. So once the agent choose to do the create, and then the reward equals to reward ground truth minus the cost create. And also if we choose the defer action, the reward function is composed of reward ground truth minus the defer cost. Therefore, the deferral, especially we need to focus on the deferral action because deferral is an expensive action. Choose it only when it is worth paying, because our human beings cannot always be asked for the agent's help. And the policy therefore learns selective execution, avoid needless deferral on easy or some like low risk cases, and escalate on some like hard or high risk cases where internal consensus may still be wrong. So once we define this kind of reward function, we can jump into our learning paradigms. Here we define this kind of dual loop learning paradigm. We want to decouple when to ask from how to improve, because we have two goals. One is to enable the model with ability to decide when to ask. Another is once we get the feedback from human beings, how can we further improve the LLM's reasoning capability? Therefore, we just decouple these two objects. And the key principle is separate short-term decision-making from long-term capability growth to avoid conflating being conscious with being competent. So here we define two loop because it naturally can be divided into two parts. One is the inner loop, which uh, which is like the policy optimization, learn when to defer, train the metacognitive controller to choose among evaluate, create, or defer. And the object is to maximize the expected utility, like the task success minus the inquiry cost minus the failure risk. And the outcome should be a boundary policy that escalates only when autonomy is likely to fail. And the second part is about the outer loop, because we already get the feedback from humans. How can we further improve the LLM itself? So they fine-tune the base solver on these trajectories to reduce future uncertainty and errors. And the outcome should be the system's competence expands and requiring fewer deferrals over time. So the inner loop learns the boundary policy, outer loop moves the boundary. And here is a formal mathematical definition of our inner loop policy optimization process, which is a very classical GRPL objective. Like in the beginning, we will construct the groups samples, and then we just calculate this kind of advantages. After that, we can calculate the policy grading objective, and finally, we can format this kind of inner loop loss function, which is composed of the policy grading loss function, the KR loss, and also the entropy loss. And then comes to our outer loop process, because we already get the feedback from humans, like the reasonings or the any correctness revision comments or any answers. And then we can store this kind of samples offline. After that, we can use this kind of offline data to further train our model so that it can further improve itself. Okay, and now we come to the experimental part. So basically speaking, we evaluate on a lot of like LM reasoning benchmarks, such as the mathematical reasoning benchmarks like GSMAK, AIME, and AMC, which is composed of different levels mathematical problems, because we want to evaluate the LLM's reasoning when it faces with different difficulty problems. And the second one is about their general knowledge or the reasoning, such as the MLU dataset. And also the last one is about the code generation task, like the human evil. And also we compared with a lot of baselines. The first part is about the single agent prompting method, the vanilla large language model itself, the chain of thought, and also the self-consistency, which is being verified very effective. And also for the multi-agent sequential or debate paradigms, we introduced the PHP and also the LLM debate. As for the dynamic workflow systems, we introduced the DLIME, AgentProom, AFlow, and also the GPT Swarm. And comes to the LLM backbones, we introduced not only the Llama 8B, but also like the Q1, 7B, and 3B, because we want to test our framework based on a lot of different backbones. Okay, and then we get into the experiment part. So first of all, it is the main results, because we evaluate our method on here defined like 5 data sets. We evaluate it with this kind of basic settings, and basically speaking, we can see that compared with the single agent LLMs, the multi-agent collaborations perform better. Like for example, the GPT Swarm, the accuracy of GSMAK is 84%. However, for the vanilla large language model itself, it only can reach like 72%. But we can see that our HILA method can achieve the consistent best performance when we compared with different, not only the single agent systems, but also this kind of multi-agent settings. So our framework establishes a new advanced paradigm consistently parsing strong multi-agent baselines across all benchmarks. Not only this kind of mathematical problems, but also the code generation and general reasoning tasks. And we can see that for this kind of competition mathematical problems, we can also reach a relatively high improvement. Besides, we also tested several other LLM backbones, such as Q17B, Q13B, and Llama 8B with Llama 3B. And we can see that since we know that the Q1 is better than the Llama itself, therefore the performance of the Q1 model is significantly better than the Llama models. For example, the vanilla performs like 90%, but for the Llama, it only can reach like 72%. And for the 3B model, it only can reach like 45%. And even for the Q1 3B, the accuracy can still reach like 83% larger than the 72% of the Llama model. And we can see that our HILA model can consistent get the improvement when no matter what the LLM backbone it is. So after that, we should do some like deeper analysis so that we can know how our paradigm works and where is the gain comes from and how can we further improve it. So therefore, we just do the ablation study related to our training paradigms. And here we just show in the left part, we show the comparisons between different training settings. The first setting is the initial policy, which means we only build up the multi-agent framework, which can ask humans help with only prompting heuristic definition. Like we just build up our paradigms. We do not introduce any training or any like learnable method to improve it. And we can see that for the HILA itself, for the GSMK, it can reach like 88%, and for AMC, it can reach like 33%, and for LMU, it can reach like 68%. Once we introduce the DLPO training paradigm, which denotes the inner loop policy optimization, after that, we can see that the performance is nearly the same, or in some like in the AMC is maybe is a little bit lower, and for the MRU is a little bit higher. So in this way, we can figure out that the GRPO process is mainly cannot improve the performance of the HILA itself. But once we look at the exact numbers, we can find that the HILA framework is also better than all of these other multi-agent frameworks, because we introduced the human beings. So the multi-agent can ask for humans help. For example, the best score of this kind of GSM-8K is only like 84%, but our initial HILA model can still reach like 88%, because it can get the feedback from humans so that it can reach a better performance. And then we found that the DLPO cannot improve the model. Okay, this comes to the question. And then what's the effect of this kind of DLPO? And I will introduce this in the next slide. And the last part is our DLPO, which means the dual loop policy optimization, which is composed of our like first stage DLPO training and the second stage continuous learning with self-supervised fine-tuning on the feedback from humans. And we can see that once we trained the HILA model with our DLPO algorithm, it can further improve their performance like nearly 2 to 5%. So from this table, we can find that with the DLPO training algorithms, our model can further improve the performance rather when it compared with the original HILA setting. And then we comes to the right figure or right table, because we already trained the LLM itself with our DLPO algorithm. So can we still use this kind of trained large language models on other multi-agent frameworks? The answer is definitely correct. Therefore, we just use our trained large language models into the original settings. Here we just tested on three kind of models. The first one is the vanilla model itself. Like here we use the Llama 3 8B as an example. For the vanilla model, it can only reach like 72% or 8% and 57%. But once we use the trained large language models with our DLPO algorithm, it can further improve the performance nearly like 10% or like 4%. And as for also for the multi-agent paradigms like D-line or the debate, our model can also like improve the performance consistently. Like here is the 8% and also the 5% on the GSM data set, and also like 2% and 2% on the MLU data set. Okay, we already know that with our DLPO training algorithms, it can further improve the performance. And now we come back to the first question, how the DLPO algorithm works. Now we come to this kind of results. We can see the exact figures here. This table, exact table here, we can see that this table summarizes the action distribution of our models with different data sets. Here we can see that still we have three settings, the HILA itself, the HILA trained with DLPO, and also the HILA trained with DLPO. And in the beginning, we can see that the action distribution is nearly obeys the uniform distribution. Like for the evil action, the action percentage is nearly like 38%. And for the deferral action, it is still like 29%. So for in the initial policy, the action space is nearly uniform distribution. Like, but for different data sets, maybe the phenomenon is somehow different. But generally speaking, it follows a uniform distribution. However, we can see that once one trained it with our GRPO and also the DLPO, we can see that the number of the evil action is getting larger and the number of deferral action is getting lower. It's a very obvious phenomenon that the agent choose to evil more and also to choose to like defer lower. So this means that our reward function works because in our reward function, we introduce the cost reward related to the creative and also the deferral action. So after the training process, the model can know that, okay, once it cannot reason very accurate, it can decide to ask for humans help, or it can decide to revise its original last round's reasoning. So in this way, we can find that with our training algorithms, the model gradually learns when to defer for humans' help. And once the model already learned from the human bike, it will continuously reduce the times to ask for humans' help. So in this way, we can figure out that how our algorithm works and how it can affect the agent's decision. So after that, we should also to figure out how different capability levels of different humans affect the multi-agent framework. And therefore, we just tested several definitions of human beings. Because currently we want to introduce a human proxy to replace the real human beings because with the consideration of the cost, because we cannot always introduce a human to solve all of these like hundreds or thousands of problems. Therefore, we just introduced the GPT strong LLM reasoning model as a human proxy. Therefore, we just tested several types of GPT with like GPT 3.5 Turbo and also the GPT 4.0 Mini and also the GPT 4.0. And we can see that stronger human proxies consistently yield better HILA performance across benchmarks. And also the HILA therefore depends on both accurate deferred decisions and high quality external guidance. And we observed that since the GPT 3.5 is a little bit lower performance, so the performance of the GPT 3.5 is nearly the same with the Llama 3 LB itself. Therefore, although we introduce this kind of human beings, but it cannot work very well because it cannot broaden the LLM's reasoning capability since the human beings is not that much smart. So once we want to have a better performance, we need to introduce a stronger human beings or a stronger human proxy. And then we need to further explore the effects of the number of agents and also the effect of the number of rounds, because we can define like different agents and we can define like different number of rounds. And basically speaking, our experimental result settings, we just defined the agent equals to 3 and a round equal to 3 as a basic setting. And here we just further tested several settings of agents and rounds. As we can see that with the increase of number of agents, there shows increased trends and then it gets smooth. So the performance improves as the number of agents increases, but gradually levels off as the collective becomes larger. And the performance also improves with more collaboration rounds at first and peaks at a moderate depth and then slightly declines with like excessive iteration. So we also can, we just also presented the input tokens, output tokens, and also the total tokens of different settings of agents. And we can see that with the increase of with the increase of agents, we can see that the tokens also increased and the performance improves as the number of agents increases, but gradually levels off and the token consumers also get larger. And also with the increase of the rounds, the input token and output tokens also get larger. And also we need to figure out that since we introduced the cost reward of the deferral action and also the creative action, we need to figure out how this kind of cost reward affect the multi-agent's performance. Therefore, we just did this kind of analysis experiment. We just set the cost defer with different numbers such as 0.1, 0.3, and also 0.5. And we can look at the right table first. We can see that in the beginning, once we set the deferral cost equals 0.1, we use this kind of rewards to train our model. And then we can see that the defer action equals to like 27%, and the evil action equals to 35%, and the creative action equals to like 38%. However, once we enlarge the cost defer, we find that the defer action number is a little bit lower, like only like 5% choose to defer for humans help. And nearly half of the agents choose to evil one of others agents, like to directly copy other agents' reasonings or answers. And nearly 40% agents choose to revise its last round's reasoning itself. And we can see that with the increase of the cost defer, the performance not always get larger or also not always get lower. It is like deferral cost acts as a control lab for collaboration. Higher cost discourages deferral, but overly large cost may degrade final performance. Like their 0.5 cost is too much. So we need to choose a very carefully designed or carefully tested cost defer so that we can achieve the balance between the performance and also the cost. After that, because in the above analysis or in the previous experiments, we do not really introduce the real human beings. However, our model is flexible to both the GPT-style human proxy and also the real human beings, so that to validate the framework remains effective when the external expert is replaced by real human beings, we conducted a real human in the loop study with real PhD level experts. We just hired more than 20 PhD students, which from like CS department, EE department, math department, also like biomedical department. And we hired this kind of 20%, 20 like PhD students to create our own data sets. And we just constructed a subset of the GSMK, AMC, and also the MMU dataset so that we can have the real human bike. And here we just also reported the performance of the large language model itself. Like for the Llama 3-8B, on our constructed dataset, it only can reach like 58% on the GSMK dataset and also like 16% on the AMC dataset. And once we introduce a GPT level models like GPT-4 mini or GPT-4o, it can further improve the performance. And we can see that our real human beings, our human experts, can achieve a very good performance. Because for the PhD level students, they are more good at to solve the GSMK or even the competition mathematical problems AMC. But for the MMU dataset, because it's composed of some like historical problems or some like general knowledge problems. So even for some like PhD students, it cannot always know all of this kind of information. So the performance cannot larger than like 90%. So based on this kind of constructed data set and with our real human experts feedback, we did a lot of experiments. The first one is we just replace the GPT proxy with our real human beings. And then we can see that with our real human beings, it can further improve their performance. Even we know that the GPT-4 is a little bit strong, but with our human experts, it can further improve the performance, especially on some hard tasks like the competition mathematical problems, AMC dataset. It can reach like 30% improvement. And also for the MLU dataset, it can also like improve like 8% gain. So stronger reactive experts consistently lead to better downstream performance with real human experts achieving the best overall results. This showed that after learning when to defer, HILA's final performance still critically depends on the quality of the external assistance. And expect for the AI agent can ask for humans' help. Our humans can also provide some guidance in the beginning because we can inject some priori knowledge into the system so that the multi-agent systems can learn from our priori knowledge. Therefore, we introduced two extra settings. We just inject the human's ideas in the beginning. Before the agents get the questions, we also input the solving idea from humans. And also we can also input the humans' full reasoning with the answers in the beginning. And we can find that with the proactive idea in some of the data set, it can further improve the performance. And once we can provide the original like full reasoning, it can reach a nearly very good performance. Even when we compared it with some like good settings like the human experts as reactive expert only. So proactive human guidance is effective only when it provides sufficient rich information, while coarse high-level hints yield limited and consistent gains. And providing a few human reasoning trees at the initial stage delivers the strongest and the most consistent improvement across all benchmarks. Just to our conclusion here, we propose HILA, a human-in-the-loop multi-agent framework that equips agents with a metacognitive policy to decide when to solve automatically and when to defer to external expertise. To support both short-term decision quality and long-term capability, we introduced the DLPO algorithm, where the inner loop uses GRPO for cost-aware deferral control, and the outer loop turns expert feedback into continual learning signals. And our experiments part showed that our model consistently outperforms strong autonomous multi-agent systems, while training progressively reduces unnecessary deferral and improves the backbone's underlying reasoning ability. And also we provided our paper code and also data in our website. In the future, we just want to further expand our work from three aspects. The first aspect is about the multi-level human collaboration, because currently we just directly ask of humans help and we directly get the humans feedback. However, later we can decide when to ask of humans help from a multi-level perspective. Like we only ask the human to generate some critical information about corresponds to specific reasoning steps. And then comes to the second part, we want to introduce the lifelong capability, acquisition from interaction, build memorial, retrieval, and also continual adaptation mechanisms so that expert interventions accumulate into reusable skills, enabling the system to require less supervision over time. And last but not least, we should introduce human-aware trust, cost, and alignment modeling, develop collaboration policies that explicitly reason about intervention quality, human expert, trust, collaboration, and safety, making human-aged systems practical for real-world deployment. And thanks so much for your listening. And once you are interested in the research agentic LLM systems, multi-agent system LLM support training, or also the multi-agent reinforcement learning, please contact us so that we can further discuss on the multi-agent systems or the multi-agent collaboration with humans. And also with thanks to the last AI talk. Thank you, everyone. Do you have any questions?
Thank you, Wei, for the great presentation. I think this is really solid work. And also I think the topic the multi-agent collaboration, multi-agent and also the human agent collaboration, I think this is a really interesting topic, receives lots of increasing attention these days. So maybe I can start from some of my questions to use the privilege as a host. Actually, my first question is about the metacognitive thing you mentioned. I think it's also the core part of this paper. I'm just wondering, is there, maybe I lack some knowledge about this, but I think there are three levels, right? The evaluate, create, and defer. Is this from some literature? They define this kind of three metacognitive actions, or just this evaluate, create, and defer? Is it from some literature?
Oh, yeah, that's really a good question, because actually the original idea is motivated by some cognitive science, because I read some cognitive papers where they mentioned that how can we evaluate the uncertainty about its own reasonings with other agents' reasonings? They said that we need to measure the uncertainty of not only the reasoning itself, but also the uncertainty or the consistency between different agents. So that here we just introduced the group level consistency evaluation and also the self-reliability evaluation from the agent itself. And also they mentioned that there are a lot of comparison signals very important for the decision, how can we compare the reasoning details between different agents so that we can get a better evaluation about the reasoning steps and also the confidence levels and also some the uncertainty signals. Yeah, so this kind of design is originally inspired from some cognitive literature.
Got it. Good. I see. And I mean, is there any order of this? Because I think probably we first do planning or create, right? And then we do deferral evaluation. But maybe it doesn't matter, I guess, in this work. Like,
Oh yeah, actually, the actions, the level of the actions is the same. Like we do not want to introduce any like priority orders of these kind of actions because we want the model very freely to do the decision because we can regard the agent as ourselves when we face a problem and when we have our first round solution and we already look at other people's solution. At this moment, I will choose to maybe I found that, okay, maybe I made a mistake. And then I found your reasoning is more reliable and you fixed some like minor errors which I made. At this moment, I will choose to trust your reasoning so that I will choose to do the evaluation action. However, once we find that maybe most of the reasoning are wrong, but I already know the detailed process or I already know which parts of the reasoning are wrong. At this moment, I will choose to do the revision based on my last round's reasoning so that we can choose this kind of create action. And the last, once we found that every agent can, the results of the different agents are totally different, there is no any majority answers. At this moment, I would choose to ask for humans' help because
yeah,
our with only with our model agents we cannot solve this problem by ourselves.
I got it. I got it. Maybe one follow-up question about this is, actually, like before listening to your talk, I was wondering like if this kind of learned metacognitive policy can well adapt to different tasks and domains. I think maybe you did the experiment on this, right? Like because you did different different data across different domains. So it seems it works. So I'm just
Oh,
wondering like because I think actually for different tasks or different domain, probably even if you ask a human to solve the task, maybe it has different metacognitive steps, right? So um, is there any intuition like why it works, like why it can well adapt to different domains? Like you don't need to learn a single policy for each domain separately. So just wondering.
Yeah, yeah, that's really another good question because in the beginning, we do not consider to only train only one meta policy for a specific data set. We just want to train for different data set. We just want to like learn a separate meta policy LoRa parameters so that we can apply it into a lot of different tasks. But later we found that it's very interesting. We just merged all of these kind of data set together and also we constructed our data set together. And we use this kind of combined data set to further train with our methods. We found it works. It's very amazing. And then later we just combine to analysis this problem. I think this one of the contributions should comes from the state-space definition because we we should first introduce the reasoning context itself, which is composed of the task context, the self context, and the peer context. We noticed that if we do not train the model, we just build up this kind of prompt with our context. The model is very hard to recognize the difference between different contexts. But later we found that even without this kind of external like structural cognitive information, we introduce this kind of reasoning context, it still can reach somehow good results. And then we found that since we introduced the non-verbal process and we just introduced a very well-defined reward function, and after the trained, the reward signal can go back to the model itself so that it can enforce the model to recognize the difference between the current reasoning with other reasonings. Therefore, we found that once we introduce a non-verbal process, the model can further focus on some details about the context information. And later, once we introduce this kind of structural cognitive information, because we provide a very templateable structural information, which is composed of fixed template with the cognitive information. So this kind of structure is very stable. And the only difference is the exact values about our cognitive information so that the model can learn the basic relationship between different signals. And when we combine these two kind of information together, also trained with our well-defined reward function, so that it can work. Yeah.
Got it. Thanks for the answer. I think it's it fully makes sense.
Yeah,
and also maybe another quick question is, have you ever tried to merge this kind of two levels together in a single level? Like you merge these two objective functions together, because I think you have two levels, right?
Yeah.
Right.
Yeah.
Like I think the main, like I can think about the reason, like for instance, maybe the reward will not be that sparse if you split them into two stages, and also maybe maybe the task will be easier. But I'm just wondering, what will happen if you merge these two in a single objective? Like will it still work?
Okay. Yeah, this is good. Also another good question, because this is related to our general design. Because in the beginning, we need to consider one question is when the model decided to ask for humans help. So when we consider this kind of question, we should introduce one action as defer for human. Therefore, they should have a discrete action named defer for humans help. At this moment, if we just combine these two stages together, that means we have two kind of action in space. One is the revising, another is the ask for humans help. So we just deleted this kind of evil action, because once we combine this together, each of the agent can choose to directly generate the next round's reasoning or to choose to ask for humans help. So the only difference is the number of the actions. But I think that we analyzed that if we design in this kind of combined way, it can mix the contributes of this kind of two stages. One another advantage of our work is we just do a little bit of good credit assignment, because we decompose this kind of two stage. For this first stage, it mainly need to figure out when to decide defer for human and when to trust one of others and when to do the revision. And this is based on the overall constructed structural state space with the uncertainty information, with the comparison information, so that we can enhance the model's high-level decision ability. And after that, we can focus on it, how to improve the further ability. Yeah, I think this is the main difference.
Yeah, I got it. And I definitely think based on the experiment, it also shows the benefit of this split it into two stages.
Yeah,
and also
yeah.
considering the time, I guess I will pick several questions from our online audiences.
Yeah,
and also
yeah.
I think actually some of their questions also aligns with my question. Actually, maybe one question is still about this human intervention. So based on my understanding, I guess the human intervention in your paper is selected or I should say like triggered based on the policy reward. Is that correct? Like basically, I mean, the question from the online audience is actually asked like, what is different between you actually just look at the ground truth? Like if it's not correct, then we ask human for intervention. Actually, I also have similar question. Like for instance, I guess there is a multi-agent debate. There are also some other rules-based human intervention. So for instance, if different agents have disagreement, then we need to ask for human for intervention. Or if the uncertainty of a decision is too high, we should also ask human for intervention. So actually, I mean, could you please elaborate more on this? Like in your work, like what's the difference about this, when to ask human for intervention, and what is its benefit in your using your method?
I see. Yeah. Thanks for the question. So for the first question is about the, I think this is related to the contribution of the real human beings or the human proxies. As you mentioned that for some data sets, we have the ground truth answers, but for some other data sets, we do not have the whole reasonings. If we only provide the answers, it is relatively hard for the model to know what happened, because we are not only to get the final answers, we need to also to generate a very compressed and with high information compressed and also or high information information gain, so that we can not only generate the correct answer, but also we can generate a very good reasonings. Therefore, for the human experts or for the human proxies, it can provide the reasoning information. And in our training process, we will use this kind of reasoning information to train our model. from the continuous learning process, so that this kind of humans knowledge can further improve the LLM's capability. And this is also verified from our application studies. And besides, I think that for different domains, somehow we do not have the ground truth answers. Like once we want to ask the human to assistant us to do some like works, at this moment we do not have the ground truth, and we only have the human's instant feelings. Therefore, we can get the human's instant feedback at this moment. So further, once we use this kind of data set to further train the model, later, even without any ground truth, the model still can know that, okay, I already look at this kind of similar patterns before. So in this case, I will not always ask for humans' help because I already learned from the humans' historical behaviors. So I think this is one of the main advantage of the real human beings. And the second one is about the humans' capabilities on the learning part. Sorry, I'm not quite remember the second question. Could you like just repeat again?
Right. So basically, I'm asking like maybe for different multi-agent collaboration system, right? There are different kinds of methods for decide when to ask the human to intervene.
Yeah,
like based on the disagreement or based on uncertainty. So what is exactly the benefit of your proposed method?
I see. Yeah. This is also another very good question because there already have several like related works. They just propose some like predefined or manually designed prompt methods to ask the agents to decide when to defer for a human. And also there is another paper. They manually design a rule-based system, and this kind of rule-based system can be used to solve the tasks based on some predefined code base or predefined rules. And then they introduce some like prompt definition in the prompt. Like once the multi-agent feels uncertainty or once the multi-agent feels the disagreement with different other agents, and the system asks the agent must ask for humans help. So there are some like related works did this. And it comes to our work, we do not manually design any like explicit prompt definition. We just ask the model to decide when to defer for human and when to revise itself according to itself. We do not introduce any like manually designed rules, and we do not introduce any like specific strategies. We just ask the model to learn from our data set so that it can learn the information from the reward and learn the information from the human's knowledge so that when they face the same other tasks, it knows that how can we choose this kind of strategic actions rather than with some like predefined rules. Yeah, I think this is also one of our paper's advantage.
Yeah, definitely. I'm just wondering, like, is there any exact comparison? So, for instance, if based on some predefined rule, based on some predefined rule, like for instance, at this moment we should ask human for intervention, but maybe in your method, at some step, at the same step, we don't need human intervention. And right, I mean, if there's a comparison for different checkpoint under different policy, I feel that would be super interesting.
I see.
Maybe I missed that part.
Yeah, so actually we can use this table as an example. In the beginning, we didn't train with our model. We didn't train with our algorithms with our initial policy, HILA. We can regard this as one of the related works because we didn't do any training paradigms. We just built up this paradigm with our prompt. And in our prompt, we just provide the candidate actions like the defer, evaluation, and also the revision. And at this moment, the model only can do the decision according to the prompt itself. And then we can see that for the deferral action, it reaches like 30%, 24%, or even like 19%. However, when we train with our algorithms, we do not only need to introduce any more deferral actions. The deferral action numbers is decreased to like degraded to like 70%, like also like 20% or 12%, and also even like 5%. But we can see that even the deferral action numbers degrade, but the performance get better. So I think that from this table, we can verify that with the trainable algorithms, it can further improve the model's ability when to ask for humans help and with a lower cost.
I got it. Cool, super cool. And considering time, maybe I will take one last. Maybe I will take one question from the audience, from the online audience. I think the question it's stated like this: so whether the performance improvement comes from the decision of, for instance, when to defer to a human, or the performance improvement comes from the knowledge from the outside GPT-4 expert model. So actually, I also have maybe if I can reframe, I think we can also understand like this, right? So for instance, like whether the proposed method is tries to learn a better collaboration method, or tries to improve or tries to improve the capability of the model itself. So I think maybe the question is about this.
Yeah. This is really a good question, and also this is our main contribution. The answer is both. We not only learn how to do the collaboration, but also learn how to further improve its ability. Because we introduce two learnable paradigms. One is action decision learnable process. Another is a continual learning process. And the conclusion is looks like this. So we can look at this table. With our DLPO algorithm, it can like increase, it cannot increase any like performance, because the performance is nearly the same with the original one, the original with any trainable methods. So even we introduce the DLPO one, the performance is nearly the same. But with our continuous learning, it can further improve the models itself. And we can see this from this table. Once we trained with the continuous learning on our feedback data set, it can improve nearly like 10% on different data sets. So that we can have the conclusion that the main gain comes from the continuous learning. But at the same time, we can find that once we introduce the policy learning algorithm, and we find that the deferral action numbers degrade and the evil action numbers increased. That means once we can introduce this kind of policy learning paradigms, the model learns somehow the trade-off between the cost and the performance. And based on this kind of collaboration, based on this trained model, we further do the continuous learning. That means we can combine the policy learning with the continuous learning together, so that the model can not only learn when to defer, but also learn from the human's feedback. And in this kind of closed loop, the model can continuously improve itself again and again with continuous generated feedback, and the model gets smarter, and then it will reduce the times to ask for humans help, so that it can further improve itself. Yeah.
I got it. Super cool. Considering time, I guess maybe we can stop here. I think also where you mentioned several future directions, I think they're all very important and interesting. I also have, maybe I still have several questions, but we can discuss offline. And also for online audiences, if you have any questions, please feel free to email to us or to email Wei. So we definitely we can have more discussion and engagement later. Thank you very much. Thank you everybody for coming, and thanks Will again for your nice presentation. Thank you.
Thank you all.